Thank you. Yeah, so good afternoon everyone. How are you doing? You alright? Yeah? Had lunch? Okay, so let's start. Are there any questions or concerns regarding anything we discussed so far? Right, so this is a brief summary of what has happened. We have observed that the feasible region of any linear program, which could be the empty set by the way, is a polyhedron defined as the intersection of finite number of spaces. And furthermore, these features are convex sets. And the way we prove complexity is we prove these two steps. One is half spaces are convex. And secondly, the intersection of any number of convex sets is a convex set. I actually want to quickly write down the proof of the first one because there is a certain point I want to remark on. So let's just do that. Right? So what does it mean to say half spaces are convex? So let's say this is a half space. It is all the points x in x bar, let's say, in Rn, such that A transpose x less than equal to A. So why are these fellows convex? So what we do is we take to show that this is convex. We need to show that there are two. We take 2 points, then the convex combinations are also in the half space. So let's just do that. Supposing x prime and x double prime are 2 points in the half space. Yeah. And let's suppose lambda is some number in the interval 0, 1. And let's say x bar is lambda times x prime plus 1 minus lambda and x double prime. And our goal is to show that this fellow is also in the half space. Okay. So we argue that x bar also belongs to the half space. Right? Belonging to the half space means satisfying this inequality. So let's see. So lambda times x prime plus 1 minus lambda times x double prime. Right, this is exactly this we want to show belongs to the half space. So that means if I multiply this by A transpose, our goal is to show that this is the same equal. So let's do the math. Lambda times A transpose x prime plus 1 minus lambda times A transpose x double prime. Yeah, that works. This is scalar. We know that this fellow is actually less than equal to beta. We know that this fellow is less than equal to beta. Yeah? Because x prime and x double prime are in the half space, so they satisfy A transpose times itself less than equal to beta. So now what do we do? So what are we tempted to write? less than equal to, you are tempted to write, this is less than equal to lambda times beta plus 1 minus lambda times beta. Why can you do this? There is a certain point here. Why can you do this? Because lambda and 1 minus lambda are at least 0. Right? I mean, this is a point that will come up in the course a lot. So that's why I want to highlight this point. Right? The only reason we are able to do this is because both these fellows, since lambda and 1 minus lambda are both normal. Right? Otherwise, you of course cannot write this. You actually not filtering. Right? And then, of course, it goes through. Then this is exactly just lambda. So we are done. Right? And this is, of course, A transpose X naught. So therefore, A transpose X naught is equal to beta, and we crucially use this fact. Without this, things may go through. Right? And that is something that's going to come up a lot of times in this course. Questions, concerns, all good? Right, so therefore, half space line be convex, very good. So what we are going to do next is we are going to move towards, remember that discussion about the corners. So let's try to make that precise. I think at this point I vaguely remember what the thing looks like. So somewhere here is 4.5, somewhere here is 7, somewhere here there is this is 6.5, this is 5, and this is 6. Okay, and this is minus 1. Should work. 3 colors, that should be enough. So that's only 9. Okay. So this line goes into here, I think. We have 7 and 7. That's this line. And then we have minus 9 and 5. And the 3 points that we 5 points that we observed at the corners are 0, 0. This cell is supposed to be 4.50. This cell is supposed to be 5, no, 0, 5. This cell is supposed to be 1, 6, I think. And of course, my drawing is really bad. This was supposed to be 2, 5. Okay, fine. That's right. This is supposed to be 2, 5, which makes no sense because like okay. Sure. Yeah, so do the adjustment. Right, so that was our constraints, if I remember correctly. What is this? The other one is 2x1 plus x2 less than equal to 9. The other one there is the pink one, that is x1 plus x2 less than equal to 7. Then there is the orange one, which is minus x1 plus x2 less than equal to 5. And then we add the two white ones, x1 and x0, and x2 and x0. Is that right? And of course, I did not write the maximization. Anyways, so the point is, what exactly do we mean by these corners, right? So this region, this set is a convex set. The feasible region is a convex set. In the particular case we are looking at, is this convex set. Right? So what is so special about these so-called corners with respect to convexity? So you all know what linear combinations are. Have you come across convex combinations? No? Okay. So let's talk about convex combinations. Convex combinations are exactly this. Okay. So convex combination of 2 points is simply lambda times if the points are x prime and x double prime. Then convex combinations are exactly lambda times x prime plus 1 minus lambda times x double prime. All such possibilities. So for all lambda between 0 and 1. This is a set of convex combinations of 2 points, right? And if you go back to our earlier discussion, this will give you exactly the line segment joining these two. Okay. So now, can you think about convex combinations and the points you see here in our feasible region? Is there something special about the corners? Something that's not true for any other point in the feasible region. What is so special about the corners? Right. So what Aditya is saying is that if you take any corner, you cannot write that corner as a convex combination of 2 other points. By other points, you mean they are not the same. Because of course, every point x bar is equal to 1 times x bar plus 1 minus 1 0 times x bar. Sure, this is an uninteresting convex combination, right? So, by proper convex combination, we mean neither lambda nor 1 minus lambda. By proper convex combination, basically, I don't want this kind of stuff, right? I also don't want half times x bar plus half times x bar. This is also uninteresting. You have not done anything interesting, right? Okay. So, by proper convex combination, I mean that neither x prime nor x double prime is the same as the point you are going to write down. So x bar equal to lambda times x prime plus 1 minus lambda times x double prime, where lambda belongs to 0, 1 is a convex combination of x prime and x double prime. Okay, that's the special convex combination. It is proper, or rather interesting. It is a proper convex combination if all 3 of these points are distinct. X bar, x prime and x double prime are all distinct. Right? For example, the point 1, 1 over here, this is 1, 1. That can be written as an interesting convex combination. I can write it as half times 0, 0 plus half times 2, 2. Yeah. So this 1, 1 is a proper convex combination of the other 2 points, which basically means that it lies on the line segment joining the other 2 points. Not at the end of the line segment, but as an interior point of that line segment. Okay? So, when you say that something is a proper convex combination of 2 other points, it simply means that that point is on the line segment joining the other 2 points. And it's actually an interior point because the 3 points are distinct. Okay? So that's what proper is referring to. And these corners are the only points that cannot be written as proper convex combinations of 2 other points in the same set. If you try to write any of these corners as a proper convex combination of 2 points, you will see that one of the 2 points is outside the set, at least one. You see that? You can take this to higher dimensions, like you can think of a 3D cube, and 3D cube has how many corners? 8. You all know what corners are. Observe that this is exactly what you mean. Right? If you try to draw any line through the corner, that line will meet the cube exactly in that point. Right? Yeah, I mean, of course, you can take a cube and draw a line inside it and going outside. But anyways, the whole line segment, if you want the whole line segment to be inside the cube, that's not possible. Right? If the corner is an interior point of the line segment, and the line segment is not allowed to be just a point, because of course the point is also line segment. So another way to put it is the formal definition, if you like, is the corners, what we will call extreme points of a convex object in Rn, are exactly those points that cannot be written as proper convex combinations of 2 other points. So S is a convex set in Rn. An extreme point of S is any element of S, is any point in S that cannot be expressed as a proper convex combination. We will use a notation. Is any point x bar in S that cannot be expressed as a proper convex combination of 2 other points, x prime and x double prime, also in S. Okay. And now, so the proper convex combination requires these 3 to be distinct. So why do we care about the extreme points? Well, we care about the extreme points because you will see, as I mentioned earlier once, whenever there is an optimal solution to an LP, there is an optimal solution that is also an extreme point. In other words, if I give you a big LP, but I told you all the extreme points of it, right? And I tell you that the LP has an optimal solution, then you can just go through all the extreme points. And if I just give you the list of all extreme points, you can just evaluate the objective function in each of them. And since I have promised you that the LP is an optimal solution, one of those fellows is an optimal solution. You can just now solve the problem by just looking at these discrete number or finite number of points. You don't need to look at this whole continuous feature. Of course, the problem is listing down all the extreme points is not that easy. So that's not how we solve it. It's nice theoretically, but listing down all the extreme points is Does it make sense? Extreme points. Okay. So what's next? So if you look at this definition of extreme points, it's very geometric in a sense, right? I mean, it's basically telling you, of course we have written it in words, but what it really means is that it's not an extreme point only if you can draw a line segment going through that point. That point has to be in the interior of the line segment, it cannot be an end. And the entire line segment has to be in your set S. That is what it means to not be an extreme point. Right? This is just the formal way of writing that. So this is very geometric. So let's think about the following question. Supposing you have a description of a polytope as a linear program or something. And I give you a point, and I tell you, so you have to convince your friend that this is not an extreme point. How would you convince them? How would you convince somebody that a point is not an extreme point? You give the convex combination, right? You just tell them, hey, this is the x prime, this is the x double prime, and this is the value of lambda. Do the math, check it, right? Okay. And they can check that x prime and x double prime are in the polytope because you're given the entire set of linear inequalities. Now, supposing you think that a point is an extreme point, how will you convince your friend that a point is an extreme point? Okay, now you can't use an extra x over prime lambda. Right, so you see that there's a difference here. The same philosophical difference that we see in many other places. Right? So convincing somebody that an extreme point is indeed an extreme point seems much harder, at least from this geometric definition. Right? Of course, in real life, if you have a 3D cube, well, if it hurts, it's an extreme point. If it doesn't hurt much, maybe it's not an extreme point. Right? But yeah, that's not good enough in math. So what we will do is we will move towards an algebraic way of looking at extreme points. Of course, we are going to restrict ourselves to polyhedra. We are not going to care about all complex objects. We are going to restrict ourselves to polyhedra, with finite intersection half spaces. So in order to do this, we are going to need some terminology. Let's do that. So I'm going to write down our visible region in the format ax less than equal to b. Yeah. So let's see what it is. 2, 1, 1, 1, minus 1, 1. Now this is minus x1 less than equal to 0. So minus 1, 0, and minus x2 less than equal to 0. So that's 0 minus 1. X, and let's write on the right hand side. 9, 7, 5, 0, 0. We have 5 constraints. 1, 2, 3, 4, and 5. So what we are really heading towards is an algebraic characterization of as opposed to geometric. So for any point in the polytope that we have drawn, which is not a perfect drawing, but it is okay for this. For any point, we are going to define the so-called tight constraints and the slack constraints. Okay? So let's consider one of the extreme points. But I can define this for any point. So I'm going to pick 1, 6. So I'm going to look at the tight constraints of 1, 6. Technically I should put one more bracket here. I'm not going to do that. It's a line. So I'm going to do that. So what are the tight constraints at 1, 6? And what are the slack constraints? So what do we mean by tight? Tight are exactly what we think tight should be. They hold with equality. And slack are the ones that do not hold with equality. Yeah? So what are the tight constraints at 1, 6? Amongst the 5 constraints, 1, 2, 3, 4, 5. Any right? I'm not doing too much. Which one? 2 and 3. Is it 2 and 3? 2 and 3 are tight. These are the tight constraints of 1, 6. And the others are slack. There is some slack here. So these are exactly 1, 4, and 5. Yeah. Let's do one more example. But this time maybe I'll take a point that is not an extreme. Let's see. Let's take some other point. So maybe can I take some point on this line which is neither this point nor this point? Somebody give me a point here. This is 2x1 plus x2 equal to 9. 3, 3. 3, 3 works. What are the tight constraints? Only the first one, right? It's only the first one. And all others are slack. Yeah. Okay, so using this concept, we are going to introduce some notation. We are also going to refer to submatrices and subvectors of these. Okay, so let's just do that. So, by A type of x bar, I'll just do examples. I'll take x bar as 1, 6 first. I mean a certain matrix. A certain submatrix of the given matrix. What do you think it should be? Type of 1, 6 is these two. So, which matrix do you think I'm going to take? The rows 2 and 3. Is that right? So, I'm going to take 1, 1 minus 1, 1. That's my A type of x bar. Okay, so we are defining A type of x bar through a few examples. A type of 3, 3 is just going to be row number 1, that's it, 2, 1. That's it. Yeah. Let's also define P type. It's exactly what you think it is. P type of 6 is basically, instead of the matrix, I'm focusing on this fellow. I'm taking the same two rows. So it's row 2 and 3, 7 and 5. And P type of 3C is simply the third element here, 5. Yeah. Let's try to see what's going on really. Observe that in this 2D example that we have. So what we first had was a geometric understanding of the corners, also known as the extreme points. Right? But now let's try to think about it. What's happening algebraically? What do you see at any extreme point? At the 5 extreme points, do you see something that is not happening at any of the other points? Sorry?
There's some tight.
Right, some. There's some time constraint. But time constraints are also there. For example, 3, 3. 3, 3 is somewhere here. 3, 3 also has a time constraint. Right? 3, 3 also has a time constraint. More than one time constraint. In particular here, you are seeing 2 time constraints. You are seeing 2 of the hyperplanes, which in this example is just 2D, so lines. You are seeing 2 lines. Let's go to 3D. A cube has how many corners? 8. What is special about those 8 points? Now think about the hyperplanes that define a cube, right? Technically speaking, half spaces, right? Every cube, how many planes, how many sides does the cube have? 6, is that correct? 6 sides. If you think of all those 6 hyperplanes and you define the half spaces in the correct way, you will get exactly the cube, right? So now think of the defining hyperplanes and the extreme and the corners of a cube. What do you see at each corner? You see the intersection of 3 planes, right? Here you are seeing the intersection of 2 lines. Yeah. Okay. Good. So that's basically what you're heading. But what does that really mean? That must say something about the rank of a certain matrix, no? Right? That must say something about the rank of a certain matrix, is that correct? Which matrix is that? It's the type matrix. It's the 8 rank of x1 matrix that we were talking about. Right? So, in fact, whenever a point is an extreme point, it's precisely because the A-type matrix at that point is a full rank matrix. That's basically what is meant, and that is what we will prove. Right, so that is the algebraic characterization of extreme points we are going to prove. Observe that this is a full rank matrix. You can write down for every extreme point the A-type and observe that all of those are full rank matrices. Which basically tells you that's the intersection of the right number of hyperplanes, and that's what's going on. So let me just write down the result we are going to prove.
So it's not this enough to be square, it has to be.
Sorry?
It's not this enough to be a square matrix.
We are going to assume the rows are linearly independent. So it is indeed going to be a full rank square matrix. So let's say P is your pointer or element, sorry, x such that x is equal to B is a polygon. Then a point is an extreme point if and only if the rank of the corresponding type matrix is n. A is n times n. That should give you the dimension of everything else. And x bar in B is an extreme point if and only if the rank of the corresponding matrix is n. And now, let's go back to your question. Supposing you know this to be true, now can you convince somebody that a point is actually an extreme point? Yeah, now it's easy, right? So this is basically an algebraic characterization of extreme points. Questions, concerns? Of course, we haven't proved it yet.
I have a question.
Yes.
If there is another constraint like x2 less than equal to 6,
Okay.
which is like cutting the 1 6 point horizon.
X2 less than equal to 6. Like this one. Okay.
So then the A-type matrix of 1, 6 will have one extra bit. Then the rank will be 3. Okay, the rank will be 4.
Yeah, rank will be 2. Yeah. Good. So let's see how much time we have. Can we move towards the elections? Let's see. We'll try at least once if we can do the other one. Okay. So let's go with the converse. Yeah, so let's assume that the rank of the matrix is actually n, and let's argue that the point is actually an extreme point, which basically means that you will have to go to the geometric viewpoint, right? Because we haven't established this yet. Space. So we'll go to the complex first. So let's suppose that the rank of the matrix is in A equal to 1. And our goal is to show that this is an extreme point. Of the polyhedron. Well, what is an extreme point? It is a point that cannot be written as a proper complex combination. Right? So, well, let's suppose you can write it as a complex combination, and then we will argue that it is actually not proper. Suppose that x bar is a complex combination of 2 points. I'm not saying they are distinct or anything. Right? We just define it as a complex combination. Supposing we could write it like this. So let's see what it will type. X bar. So this is notation here. We are just taking that submatrix and the column vector is still what it is. Let's see what we can do with this. Well, we can rewrite, we can replace this by this fellow. Yeah. Well, let's do some things that will accelerate the problem. The same force. Lambda times d by x bar plus minus lambda times well, x prime is a point in the polyhedron. So what can we say about this quantity? Since x prime is in the polyhedron, less than equal to b tight. Yeah? Yeah. So since it is in the polyhedron, well, let's remember, I mean, maybe one thing I did not emphasize repeatedly is when we are comparing two vectors when we say less than equal to, we mean component wise less than equal to, right? So since x prime is in the polygon, Of course, if you evaluate these constraints at x prime, whatever you get will be less than equal to the right hand side. Okay. So that's less than equal to b tight at x bar. And here also, are we using the fact something about lambda? We are using something about lambda, right? And because 1 minus lambda is also greater than equal to 0, we can do the same thing here. Yeah. Okay. But well, what can we do now? This is exactly b tight of x bar, lambda plus 1 minus lambda. Yeah? Oh, okay. But what do we know about a tight of x bar times x bar? That is actually equal to b tight, right? Because this is the way we define tight. These are the tight constraints. So, since we define tight of x bar in a certain way, clearly this is the same as b tight of x bar. This value is the same as this value. What does that tell you? That tells you that everything holds with equality, right? Everything must hold with equality. In particular, this must hold with equality. But remember, the way we got this is because this fellow is less than equal to this b tight, and here, yeah, this fellow is this thing and this thing. That's the way we got this, right? So therefore, if everything holds with equality, then this holds with equality and this holds with equality. If any of them is a strict inequality, then you have a strict inequality here. You all agree? Right? In fact, this value is equal to this. A tight of x bar times x prime is exactly equal to b tight x bar, and likewise a tight x bar x double prime is also the same as b tight x bar. So if we evaluate the tight constraints matrix at x bar for x prime or x double prime, you will still get that it is tight. What does this mean? Have we used the assumption we started with anywhere so far? Actually, that's a good point. The assumption we started with, where have we used this so far? Have we used it anywhere? I forgot. Have we used it anywhere? No, right? This assumption has not been used anywhere. I mean, either we use it or we do something much more general. So, what do you say by this assumption?
The solution has to be unique.
There's a unique solution, right? The full rank matrix, it has a unique solution. That's the algebra, right? So therefore, because it has a unique solution, x prime better be the same as x bar, and x double prime better be the same as x bar. This is where we are going to use the hypothesis that we started with. And in fact, this is used only here. Until now, everything we did not use this. Implies that a tight x bar equal to b times x bar as a unique solution. Right? But that means that all these three are just the same. X bar is anyway the solution to the system, right? Because that's how we define the type matrices and vectors. A type and B type are exactly those rows that hold with equality for X bar. So X bar is a solution to the system, and X prime and X bar are better with the same fellow. Well, we're done. Okay. So this basically tells you that whatever convex combination we wrote is not a proper convex combination. In other words, X bar is not a proper convex combination of 2 points in the polyhedron, which basically means that by definition X bar is an extreme point of the polyhedron that finishes one direction. It is indeed an extreme point. So now let's do the converse. Let's see if you have enough time for that. Or maybe we'll not finish it today. We'll just start and leave it with the DI. Questions, concerns about? Everybody okay with the converse selection? Right? We assume that the rank is a full rank matrix, and we prove that the one is a given extreme image. So one small point about notation. For those of you who have a copy of the book GKT or are following the copy of the book, physical, electronic, whatever, they use this notation. Rather than writing A type, they use A equality and B equality. So just imagine how confusing that would be with all the inequalities and equalities we have. If you are following the book, they don't use type. Okay. We'll actually show the contrapositive. Rather than putting the forward implication as it is, we'll take the contrapositive. We'll show that the rank is less than n then you can actually write it as a proper convex combination of two other points in the same polygon. Okay? Let's suppose that it is less than n. Suppose the rank of this matrix is less than n, and our goal is to show that x bar can be expressed or written as a proper convex combination of 2 points x prime and x double prime that are also in the polyhedron. And proper means that all 3 points are distinct. That's what we need to do.
So we are assuming that M is always greater or equal to N, right?
Yes. Yeah, you can assume that n is greater than equal to 1. Do we need that? Is the statement false without that? If n is less than n, x1 plus x2, like if I take just one line, then I will just not have any extreme points. Yeah, so I don't think we need to write this explicitly. Yeah, basically it will just imply that there are no extreme points. Yeah, so that's why I think we are not writing this explicitly. Yeah. For example, in 3D, I just draw 2 planes. But if I just draw, I don't draw, but I imagine. If I just imagine 2 planes in 3D, in the corresponding half spaces, I don't think I'm getting extreme points. In fact, the intersection of the 2 planes, if they intersect at all, it will just be one line. And all points on that line can be written as convex combination of 2 other points in the same line. So it will just not have extra points. Yeah? Okay, so this is what we need to do. Let's do an example to kind of get some idea about how the proof is going to work. So we are taking assuming the rank is less than 100, and if I go to example, I mean, technically what it means is we are considering some point like this or some point in the interior. And basically all the points in this example where the rank of the type matrix is less than n, they are basically not the extreme points. So think of any other point. It could be on the surface of the polyhedron or it could be in the interior. But it is not one of the corners. Right? So some of the constraints might be satisfied tightly. For example, 3, 3. But you can see that 3, 3, you can actually write it as a convex combination of these 2 fellows, which are also on the same hydrogen. So, anyways, that's what we're trying to do. We're assuming that the rank is less than n, and we want to show that there is some wiggle room so that we can find 2 points in the polyhedron and draw a line segment around this point, and the whole line segment will be inside the polyhedron. That's basically what it means to write a point as a proper convex combination of two points in the polyhedron. Right? So this is what we're trying to do. So we won't finish the proof today. Let's just get started on some ideas. And I will leave it as a DIY. We'll finish it on Monday. So let's just write this fellow. I mean, you all agree that we can write x bar as half times x prime plus half times x double prime for some 2 points in Rn. This much is clear, right? Definitely this can be written as for any point in Rn, I can draw a line segment around it, and I can write it as half times this point plus half times this point. That's not a problem. The problem is the 2 points have to be in the polyhedron. This is the hard part. Right? This is not difficult, but we need x prime and x double prime to be in the polyhedron. And we also need x prime, x double prime, and x bar all distinct. We need these things. So in fact, the goal is to construct 2 points like this so that everything works. Right? So in fact, the whole goal, the plan is to show that we can construct, I mean basically we can give explicit formulas of this. We can construct x prime, x double prime, to achieve all of this. This is the plan. We will show that. You can actually write down, if you want, you can write down a proper formula. Of course, somewhere we'll have to use this assumption. Right? Without this assumption, we should not be able to do this. Because we have already proved that if equality holds, then the fellow is actually an extreme point. We have already proved one direction. So somewhere we will definitely have to use the hypothesis that the rank is less than n. Right? But we will use this hypothesis and we will show that based on this, we can actually construct x prime and x double prime. They will be in the polyhedron, they will be distinct from x bar, and x bar will be half times x prime plus half times x double prime. Yeah. Okay? So, how do we do this? And how do we use this fellow? What does it mean for the rank of this fellow to be less than n? The rank is less than n.
A tight of x bar into x equal to b tight of x bar and have infinite solutions, whatever is now.
Infinite solutions, right. Okay, that is one way of looking at it. Anything else you can say? The rank is less than n. What else can you say?
There will be some column which will be written as a linear combination of.
Right. Some column can be written as linear combination of other columns. For example, let's take an example here. Right? I can write either of them as a linear combination of the other. Okay? In other words, I can take some linear combination of the columns to get the 0. Some linear combination of the columns will give me 0, the 0 vector. Right? This fellow basically implies that I can multiply this fellow by 0 by some vector 8 by x bar times some direction vector will give me 0, where d is not 0, for some d not equal to the 0 vector. You agree? There exists some linear combination of the columns so that I will get the 0 vector. Right? But some non-trivial linear combination, which means that d itself cannot be 0, of course, that is trivial. So this is what we are going to use. We are going to use the fact that there exists such a vector d. Think of this as the direction vector. So in this example, if 3, 3 is the point I am looking at, so in some sense I should be able to go in this direction, and of course the same direction in the other side, right? And I should be able to find some x prime and x double prime, so that this fellow is exactly this times half plus this times half. That's basically what we're going to do, right? So think of this point as your 3, 3. This is your x bar, and this is going to be your x prime, and this is going to be your x double prime. The reason I am choosing a point on this line is because if I choose a point inside, there are too many directions I can go in. Here I have to go in a certain direction. Right? Okay. So this is what we are going to do, and what I am going to do now is I am going to leave this as a DIY, which means we complete it on one day, and hopefully you complete it before we complete it. Yeah. So see if you can work out the details. I've already given you the main point here. There is a vector like this, for which you will get the 0 as a convex combination, as a linear combination of columns. Okay. And now you just need to use this d to construct these x prime and x double prime. Somehow this has to be useful. Yeah. Okay. So that's all for today, and we continue on Monday at 5 p.m. Any questions or concerns before we wrap up? All good so far? Okay, have a nice weekend.